Welcome everybody to a new episode of Ixxat Connect. Today, my guest is Christopher Koch, Product Manager and expert for automotive communication technologies. We will focus on two key technologies for the automotive industry, Automotive Ethernet and CAN XL, and have a look at their evolution, the current status of the industry, and of course, compare both on a deep down technical level, highlighting the pros and cons. Welcome, Christopher. Great to have you again.
Thank you, Emilio.
First of all, I'm interested in the overall situation in the automotive industry, its evolution and current challenges. Could you give us a short overview on this and put it into context for the communication technologies?
Yeah, of course. So I think probably this is best explained by looking at modern cars that are released today and then kind of try to figure out what this means for us on the technical level and also for the communication technologies within the car. So if we look at the modern cars of today, they are more and more defined by software. So there's a very funny anecdote of, for example, BMW, which has released a subscription model for heated seats. I think it was last year or 1.5 years ago. And then there was a big shitstorm and they removed this. But this is a very good example of showing us that today's vehicles are more and more defined by software. And this trend within the industry is called the software-defined vehicle, meaning that the software of a car is the main driver of its functionality. And if we look at the communication within the car or the board net setup as well, this implicates a trend of these very distributed network architectures where we have ECUs everywhere in the car. For example, one ECU, responsible for braking, one ECU responsible for a certain function, to a centralized architecture within the car where we have these very centralized high-performance computers, or in the industry they are called HPCs, which are then capable of running hardware-agnostic software. So this means the software developers at the OEMs can continuously release new software updates and then also release new features on the vehicles. And then if we look, or if we take this to the next step and look at the communication technologies within the car, what this means is that we have this switch from this distributed architecture to the centralized architecture, and this means more bandwidths and or higher bandwidths overall and more data transfer.
Interesting. So what do you think is the most important consequences for the in-vehicle networking then?
So I think in general there's one main consequence, as I just said, which is more data. So higher bandwidths and, at least for CAN, larger packet size. And now if we look, and actually this can be very well seen in this technology radar or in the development of the different technologies over the time. So if we look at all the in-vehicle networking technologies that appeared over the last years or decades and plot them against the data rate, we see that the trend is moving upwards by a lot. So we see more and more higher data rates in CAN and in Ethernet-based net.
All right, thanks for the explanation. Let's now focus on Automotive Ethernet first, which appears to be a bit more complex. Could you give us a detailed introduction on this technology?
Yes, of course. And I think this explanation is probably started best by looking at the ISO OC reference model for communication first. So we have these 7 different layers of communication. And actually the main difference for Automotive Ethernet is on the lowest layer, the physical layer. And this is quite interesting, because if we talk at Automotive Ethernet, you never know what really is meant, so there are different parts to it, but the main difference is on the lowest layer, the physical layer. And there are different physical layers specified for Automotive Ethernet. such as 10 Base T1S. We have, which is more legacy, 100 Base TX, also referenced as broader reach. We have 1000 Base T1, 100 Base T1, and we even have multi-gig automotive Ethernet, for example, 2.5 gig base T1, 5 gig base T1, and so on and so forth. So there's a lot of development here. And what actually this T1 is referencing to is that we have one twisted copper pair. So normal industrial or consumer Ethernet has 4 twisted copper pairs, and this T1, twisted one, is referencing to one twisted copper pair, and this saves weight and money.
Okay, I see. So the key difference is that we have a different physical layer, right?
Yes and no. So I wish it was this simple, but it sadly it's not. So yes, the main difference is, and this is also where it comes from, we just talked about it, lower weight, less money because less materials. So we only have a single twisted copper pair, so this is the main difference on the physical layer. But when we talk about automotive Ethernet, and also Ethernet, the whole protocol stack is referenced to. So if we look back at the ISO OSI model, there are actually differences in or additional functions in the application area as well. So not only on the physical layer, but also on the application area where we look at what we do with this data. And if we look into these application areas, there are a lot of different protocols and a lot of different standards here. For example, SumIP, which is a middleware protocol that brings the service-oriented communication to the ECU world of cars, and this allows to exchange services over IP. There's also DoIP, which is a diagnostic protocol which allows ECU to be diagnosed over IP networks. So, for example, if you want to read faulty or if you want to read error codes from the ECU, you can do this over DoIP. The automotive Ethernet stack also supports signal or PDU based communication, which we already know from CAN, for example. So we take the data or one packet, one frame, and put a lot of different signals into it. So this is also supported. We have protocols or standards such as XCP, which is for measurement or calibration, tuning some parameters over IP. And there's also AVB or TSN, which is for time synchronization. And a good example here is if you have a video being displayed in the rear seat and audio coming out of the speakers, you want to have the video and the audio synchronized. Or another example is, let's see, you put your car in the rear gear, so you want to reverse, and then the camera starts showing up, and you have a camera in the front, you have a camera in the back, you have cameras on the sides, and all of these should be synchronized. So this is where the AVB or TSN protocols are used.
So we saw that the physical layer of the 10 Base T1S appears to be competing with CAN-XL. Could you explain to us this physical layer a little bit more?
Yes, of course. And actually 10 Base T1S is a bit special compared to the other physical layers of automotive Ethernet. And this is also the reason why it is competing with CAN-XL. So if we look back at this technology radar, we saw that CAN-XL and 10 Base T1S are pretty close to each other. So similar date of appearance and also similar data rate. And while you could think, okay, they are competing because they have the same data rate. Actually, this is not the case because there are more similarities, which is why they are competing. But let's look at the norming status first. And 10 Base T1S is normed in the IEEE 802.3CG-2019. So it's an old standard. So it was released in 2019. But we now see it being used more and more, and we are also being asked about it more and more. So this is also the reason why we do this today. And the main reason why 10 Base T1S is so special compared to the other physical layers of the Automotive Ethernet stack that we previously saw is that it supports multiple ECUs in the same network. So let's very briefly look at the topology of Ethernet networks. We usually have these ECUs that are switched. So it's always a point-to-point connection, so one ECU to another. And then this may act as a switch connected point-to-point to even more ECUs. With 10 Base T1S, this is completely different. So 10 Base T1S supports what we call multi-drop bus topology. So we can have up to 8 nodes in one 10 Base T1S network. And the overall length of this network can be up to 15 meters with stubs up to 10 centimeters. And this allows very flexible and a lot of different bus topologies, very similar to CAN. So this is where the competition starts appearing. The data rate for 10 Base T1S, as the name suggests, is 10 megabit per second. And yeah, as I previously mentioned, it is transmitted over a single twisted copper pair. I think if we look at the collision avoidance, this is pretty interesting because one might ask, how does this work on a technical level? Ethernet is usually point-to-point, and we have the CSMA collision avoidance. In standard Ethernet, this will not work for these multi-drop Ethernet topologies. And here we have a completely different collision avoidance, which is called PLCA. And this is for physical layer collision avoidance. And how this works is, so it's not mandatory by the standard, but usually everyone uses this because this is what it is made for. And how this works is that we have very untechnical. I think if we wanted to explain this in a detail, we would need to make a separate video out of it. But very simply, each node in the network is assigned transmit opportunities and a time slot. So it's a round-robin procedure where you have the opportunity to transmit some data. And the main application areas within vehicles we currently see, and this is where these multi-drop bus topologies really come into play with their advantages, is in, for example, sensor or actor networks, where you have a lot of different sensors and actors, or in these zonal architectures within vehicles. So you, for example, have a door zone, or you have a rear zone or a front zone.
Thank you for those very detailed insights. Now let's jump over to the CAN side of things. What is CAN XL and where does this exactly come from?
Yeah, let's jump to the CAN word. So if we look at the very beginning of our talk of today, we saw that we have this trend of the demand for more and more data, right? So CAN XL actually is the answer of the CAN world to this evolution or to this development. So if we also look at the technology radar we saw in the beginning, we had CAN in the 80s, CAN FD in 2015, and more or less today we have CAN XL each time with a higher data rate and a higher payload. The current status of CAN XL, this is why I meant more or less today, is that it is specified in the CAN norm, the ISO 898-1, and it has just very recently been published and revised, May of this year, May of 2024, and now it is officially a standard and we can use it.
That was interesting. Could we get a little bit more technical and let's talk about the differences between CAN FD and CAN XL?
Yeah, sure. Let's look at the differences. I think even though we very briefly will look at the differences, let's look at what is similar to CAN FD first, because this is also very important because it's not a completely new technology, right? It's the next generation. So I think one of the really very good things about CAN XL and the key features is that it keeps the main structure And the main functionality, also the collision avoidance, the bus access, very similar to what we have with CAN or CAN-FD, so this arbitration. And the main structure, the core concepts remain the same. However, there are a couple of differences, and I think the most dominant and also, which I just said, the most important ones is that we have a higher data rate at up to 20 megabit per second. Even though I have to say that in real world applications, we usually see this being used at 10 megabit per second. So typically the 20 megabits that are possible are not really used. So usually this remains at 10 megabits. And the second big thing is that we have a higher payload. So we have up to 2048 bytes that the users of CAN-XL can use. There's also an important thing that is being introduced, which is an updated identifier usage. So usually in CAN-FD, or this is in CAN-FD and CAN networks, we had this CAN identifier, which has basically two purposes. So we have the first purpose is to act as the priority for bus access. So the lower the message ID, the higher the priority to access the bus. And the second one is the message of the ID. It's the ID of the message itself. So this was implemented to know what this message is for. And in CAN-XL, this is being split up into two parts. So the message ID remains to be the main factor of the bus access. And we have a new ID, which is called addressing ID. It's a bit further back in the CAN-XL frame. And this is now used to set the ID for your message. Next, we have a new feature or a new data field, which is called service data unit types. And these are actually used to interpret what is within the CAN-XL message. Because CAN-XL is backwards compatible to CAN-FD and CAN, and the payload is big enough to tunnel Ethernet frames. We need to know what type of data we transport here. So this is what these server data unit types are for. So I just mentioned this. In theory, it is possible to transmit Ethernet frames over CAN-XL. And the next big major feature or innovation of CAN-XL is the introduction of these virtual CAN IDs. And this allows you to segment one CAN bus into several virtual networks using an 8-bit VCID field. And in theory, this allows support of up to 256 logical networks within one CAN-XL network.
Thanks for giving us that detailed overview. As CAN-XL is rather relatively new, I'm wondering to myself, is this technology already being adopted in vehicle usage?
Yeah, that's a very good question, and I think it's very interesting for all of us. I think, honestly, now that the standardization and the normalization is finished, we will firstly expect also from the semiconductor companies the first IP cores being implemented, and also then the first controllers being released, and then also for the whole testing suppliers and toolchain providers to then also start developing this toolchain. And I think then we will see the OEMs and the tier ones starting the first new project, and then we will probably see it also appearing in the first vehicles sooner or later. I think, to be honest, we don't really know how quickly or even if it is going to be adopted. I think we're in a pretty dynamic situation at the moment, also looking at the Ethernet side of things. And I think we just have to prepare for both. So we have to be ready for both, and we will see what is going to be adopted.
All right, this totally makes sense to me. If we have a closer look now at the physical layers of CAN XL and 10 Base T1S, what are the key differences?
Yeah, I think this is pretty interesting now. We saw both a bit. We had some technical introduction into both the technologies, and now, what is the difference? What is maybe the advantage of the one over the other? And I think we should explain this a little bit. So I think let's look at the transmission speed first. 10 Base T1S had this 10 megabit per second fixed, so there's no change here. And it's 10 megabits across the whole frame. With CAN XL, we have this CAN concept of a data rate switch, which means we have the slow mode for arbitration and end of field, which is below 1 megabit per second, so very similar to CAN FD. But for the larger amount of the packet or the frame, we have up to 20 megabits per second. So a bit or double as much as we have for 10 Base T1S. But as I said, usually 10 megabits per second is used here. The next major difference is in the collision avoidance and bus access. So we have this PLCA, physical layer collision avoidance with this time slots or transmit opportunities, versus the CSMA carrier sense collision avoidance in CAN that we all know and that works very well. What's probably very interesting to a lot of also network architects out there is the question of which is more efficient. Because usually you in networking technologies, you always have an overhead of the message, and you have the packets or the data that's in there, and how much overhead is there. What is the efficiency? And actually, if we compare this for CAN XL, so assuming 100% usage of the data fields and 10 megabit per second, CAN XL has a 93% efficiency, and 10 Base T1S 97.5% efficiency. And this is mainly because CAN XL has a higher overhead compared to 10 Base T1S. The next thing that we can compare is the topology. And here it's pretty similar. I think CAN XL overall is more flexible, so we can support more nodes, and the stubs can also be longer. But in general, both support these multi-drop network topologies. I think the next major point that we can compare between CAN XL and 10 Base T1S is the determination. So how deterministic is one or the other protocol. And 10 Base T1S is actually determined by the duration of one bus cycle, and there's no prioritization. While CAN XL is determined by the duration of one CAN frame. And prioritization, because of this message ID, is possible, and therefore CAN XL is a lot more deterministic than 10 Base T1S. And I guess the last major thing that we can compare is the application layer. So earlier you saw this, we saw this ISO OSI model with the different layers and the whole Automotive Ethernet stack. And for 10 Base T1S we can use this whole Ethernet stack. So we have TCP, IP, UDP, and all of the nice things that are above. For CAN XL, this is for the CAN world not the case. However, because CAN XL has a payload that's high enough to tunnel Ethernet frames, we can also have these, or you can also have access to this Ethernet world over CAN XL.
That's quite an abstract level of comparison. What does that mean exactly for the application side of things?
Yeah, I think it's also a very good question. To be honest, we do not exactly know at the moment because 2 new technologies, 2 new standards. We'll see how this will emerge. I can maybe anecdotally give 2 examples that I have seen for these, for both of these technologies where they are used, and maybe you can see on each of these examples where the strengths of each of the technology is lying in. So let's look at an example application for 10 Base T1S that I found to be very interesting, and that I can present you very briefly, which is in the field of a door zone. So if we look at a door of a modern passenger car today, we have door handles, we have a window regulator, we have speakers, there might be in very higher segment cars even cameras on the outside door handle to see some video for parking purposes. You might have ambient lighting and so on and so forth. And previously, you might have a lot of different networking technologies for each of these different applications. So, I don't know, for the window regulator, a LIN network, and for ambient lighting, I don't know, maybe CAN, or for door handle. And 10 Base T1S has the potential of being the network to address all of these different sensors and actuators in a door zone, for example. So you wouldn't need to have a lot of different networks anymore going and all of the cabling as well going into the door, but only one very small and simple twisted copper pair, which is then split up to each of the sensor actors to have in this door zone. And this is a extremely good application and a very big benefit to all of the engineers out there. And then on the other side on the CAN XL side, I saw a very interesting on a conference once application as a backbone bus for in heavy duty machinery. So let's say in heavy duty machinery you have a lot of different ECUs, sensors and actors as well. You might have CAN, you might have CAN FD, maybe there's some 10 Base T1S or some Automotive Ethernet in general there, but usually you don't have these super high bandwidths in comparison to passenger vehicles. And here CAN XL has the opportunity, because it's so backwards compatible to CAN and CAN FD and can also tunnel Ethernet frames, to be used as a backbone for combining all of the different technologies and tunneling this for data transmission. So I think there are two different types of applications, and we are quite excited to see what will be adopted in the market.
As we now have a great understanding of both technologies, I'd like to ask you to outline the solutions that HMS Networks provides in this context. What are the potential communication solutions that HMS will provide to the market?
Yeah, I've been expecting this question for this whole interview, and I can surely explain to you what we are working on or what we are looking into at the moment. So in general, both technologies, as I mentioned, are very interesting and important to us. So we are working on both of the technologies. For example, within the HMS group, we are currently implementing, and I know it has successfully being tested at the CIA Plugfest as well, an own CAN XL IP core, which maybe there will be some new products in the future. Let's see what's coming up in the next years. And on the other hand, we in the last months have developed a 10 Base T1S computer interface prototype, which is already out there for some customers to test. And anyone that's also watching this video that's interested can contact us or me directly to also receive a copy of this prototype to test it. What I can already tell you, what the first big product will be supporting Automotive Ethernet, very specifically 100 and 1000 Base T1, is the new Ixxat mobilizer, which is our big automotive testing platform with CAN FD, with LIN. It can act as an EtherCAT slave. It can do signal manipulation, REST bus simulation, even data logging is mainly used in test bench applications. And this will be released within 2025.
Thank you, Christopher, for those stunning insights. And thanks again for being our guest today. I hope you enjoyed watching this episode. See you next time.